was the quiz one paper?
Good morning, sir.
It was good. It was pretty easy.
Easy. It was adventurous, right?
Yes, sir, quite adventurous because in one question I have to uh, go through that question 3 times. I have changed the option 3 times.
Which question?
All the questions
Okay.
means we have to go through the questions very thoroughly.
Okay, yeah.
And in one question I did silly mistake, like the last question in which we have to subtract the difference and then project the D attribute. In that I counted the duplicate tuples also. So I gave the answer 5 and the answer was 3.
Three,
So
yeah.
I did
Number of tuples, yeah.
mistake. It was very silly mistake. Yes, I did that also.
Okay. You can practice more, yeah. So that is
Yes, sir.
one of the relational algebra question, right? So yeah. So in the live session also we discussed that projector will
Yes,
remove
sir.
the duplicates value. Yeah. Okay. So any other student, any feedback? No feedback. It was easy.
Sir, all the questions were discussed in the live session. So yes, it will be pretty easy those who attend the live sessions.
Question was not discussed. The concept was discussed, right?
Concept was discussed. Yes, yes, sorry.
Yeah. Okay. So any other student, any feedback? Okay. Okay, so no problem. So today we'll start with the week 6. So before that, we'll take one question from week 5 just to revise the concept of week 5 because that is very much required for the week 6 part. Okay. Yeah. So Subhendu, can you present that question?
Yes, sure.
Thank you.
Sorry. Yeah, my screen is visible.
Yes.
Hello.
Yes, sir, it is visible.
Okay. So, okay. There is one relation R and attribute sets are A, B, C, D, E, and F. And the functional dependency given AB determines CD, C determine D, D determine E, and E determine F. First, you have to find candidate keys and prime attributes. So, anyone want to volunteer how to find candidate key? Okay, no issue. Am I audible, right?
Yes, Subhendu, you are audible.
Okay. So, given functional dependencies are AB determine CD, C determine D, D determine E, E determine F. There is one method of finding candidate key that you can find easily candidate key, that those attributes not present in right hand side must be part of candidate key. Like if you see C D is present, so C D is present, E present, E present, F also present. AB is not present in right hand side, so AB is the must part of the candidate key. So let's closure of AB. So AB closure will be AB determines CD. So A, B, C, D. Then C determine D, we will get C determine. From D determine E, we will get E. So A, B, C, D, E. E determine F, so we will get A, B, C, D, E, F. So AB is a candidate key. So with the help of AB, we can find all the attributes. So AB is a candidate key. So candidate key is AB. And the prime attribute will be A and the B. So AB is candidate key and the prime attribute will be A and B. So I hope everyone got it, how to find candidate key and the prime attribute.
So primary would be A or B or A and B.
A or B.
Prime attribute will be A and B. It's not together. A is also prime attribute, B is also prime attribute.
Okay. Okay.
Okay. And then we have to find lossy or lossless decomposition. Okay. So if you remember the lossless decomposition, there are three conditions. First condition, R1 union R2 must be equal to R. The second condition, R1 intersection R2 does not equal to null. And the third condition is R1 intersection R2 must be a key in R1 or R1 intersection R2 must be key in R2. So yeah. So decompositions given are A, B, C, D, E, and E, F. So yeah. So let's write R1, A, B, R2, C, D, E, or R3, E, F. Okay. So first we have to see R1 union R2 equal to R. So let's uh, 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 one relation with the help of R1 to what will be that A, B, C, D, E. Let's join R1 to and R3. So what will get R1 to A union R3 will get A, B, C, D, E, F. So first condition is satisfied. Okay. Then we have to see uh, next condition. Next condition R1 intersection R2 that there exists some common attribute. Okay. So R1 to equal to let's R1 intersection R2. So there is C A, B, and C, D. So there is no common attributes in R1 and R2. So this is a lossy decomposition. So everyone got it? Hello?
Sir, I have a doubt.
Yeah,
Here,
yeah.
R1 union R2 equal to R you have written means R1 union R2 union R3 or it is R1 union R2 only.
Okay. See. First, let's take temporal relation R1 2. So that will get R1 union R2. So what will get A, B, C, D, and temporary relation and the R3, R1, R2, and the R3. So what will get A, B, C, D, E, F. So this is the method.
Means this representation, this represents all the relations union,
Yeah,
right?
yes. If there is, suppose there are another decomposition are put, then you have to make another temporary relation like 1 and 3, and you have to join. You have to repeat this method.
Sir, then we can say that there are n number of decompositions, and union of all that gives me the original set of attributes.
Yes.
Then it is lossless.
No, there must be, satisfy 3 condition, not this. This also, this also.
Okay.
You have to first satisfy this condition also, and this condition and this condition. Then we can say that lossless decomposition.
Okay.
Sir, I just have one doubt.
Yeah.
Here, R1 and R2 represent R. Now, when R1 and R2 we added, it does not clearly satisfy the whole set A, B, C, D, E, F. But R12 plus R3 defined the whole
Yeah.
set. So
Yes.
in this case, R12 is my R1 and R3 is my R2.
Yeah.
So the intersection of R12 intersection R3, which is not phi, which is not empty, because
Okay.
in place of you have clearly mentioned that R1 intersection R2, but R1 R2 is not my set. R12 is my R1 and R3 is my R2.
Okay. See. First, you have to see R1 and R2. So see. What will you get? R1 intersection R2. What will you get?
Which is null, because there is no common element.
Okay. So
But
we can say that.
But sir, R1 union R2 does not clearly mention the whole set. So the first condition is also not true for this condition to evaluate R1 intersection R2.
So see. Okay. See.
Hello. Yes, here. So suppose we decompose the relation R into number of relations, say n, then the R1 union R2 till Rn must be equals to R. So that is the first condition. Okay. So in this case, if you see R1, R2, R3, intersection of all three decomposed giving R. So first condition is satisfying. Now, what we said that R1 union R2. So if there are only two decomposed relation, for that we have to check R1 intersection R2. Okay.
Piyush sir, for this, then my R1 is replaced with R12. So the new set of R1 is R12 and R2 is R3. So both, if you go for the intersection, which is clearly not phi, because there is some common element. So for me, it is not lossy.
No, see,
because it's satisfied. And the third intersection of R1, R2, if you go for, then it will define the set EF. So all the three condition is satisfied for me on my understanding.
Yeah. So see here. So whatever we have considered R12, that is for the first condition only. For second condition, you cannot consider R12 because there is no common attribute between R1 and R2, right?
Sir, the first condition is satisfied based on R1 union R2 union R3.
Yes.
That is R.
That is R. So that is first condition is satisfied. Now you have to take those combination of R1 and R2 in which the intersection must not be an empty set for lossless decomposition. So here, if we consider R2 and R3, there is common attribute. So we can take R2 and R3. So in that R2 union R3, so R2 intersection R3 will get E, right?
Correct, sir.
Yeah, so that condition is satisfied. Now from E, I can get EF, so R3, right? So now this R2 and R3, only if we consider these two decomposition, that decomposition is lossless, R2 and R3, but we have to check for R1 also. Then in that case, we have considered, say, R23 equals to R2 union R3. Then R23 will be C, D, E, F. Then again R2 3, then we have to check for R2 3 intersection R1. So in that case, it will be empty set, right?
Okay, sir.
Okay, you got it. So this is the lossy decomposition. Then we have to find this decomposition is dependency preserving or not. So
Miss,
yeah,
then we have to check for every pair in all n decompositions. Like
yeah, can
three
yeah,
decomposition. One, say 1, 2, 3. Then we have to check for every pair like 1, 2, 2, 3, 1, 3.
yes.
Yes. Say first you have to check all the decomposed relation giving me R or not, which in union of all the decomposed relation. If that condition is satisfied, then we have to go for second condition, and then we have to take those two relation, decomposed relation, in which we are getting the common attribute. Okay. If you take R1 intersection R2, here there is no common attribute. Then you go for R1 intersection R3, it is also not common attribute. Then you check for R2 intersection R3. Okay, so there is a common attribute. You are taking R2 and R3. Okay, so you have to check all the possible combination. But from the second condition, we can infer that, okay, so if there is a common attribute between any two relations, that two relation we can take, right? R1 intersection R2. Then we can check for the third condition.
Sir?
Yes, Prashant.
Yeah. Sir, I am Hemant.
Okay, Hemant, yeah.
This R2 and R3 are satisfying 2 and 3 conditions, but not first condition, right? But R1 union R2, that is also required to be satisfied. Right? It is only giving CDEF, but without AB. R1, sorry, R2 union R3.
First condition document, right?
Yes, sir. It is satisfying second and third, but not first.
No, so these are the only condition which you are represent to check whether the decomposition lossy or lossless. Okay, means this condition is applied when we decompose one relation into R1 and R2. So if we are decomposing this relation into say n number of decompose, then we have to check for first condition R1 union R2 union R3. Okay, so what Subhendu is doing that R12, so that is also correct, but that is applicable only for first condition to check. Okay, we cannot apply that R12 to the second condition because R12 there is no common attribute between R1 and 2, right?
Yes, sir.
So in the last session, on Thursday session, we have taken one example. In that we have decomposed one relation into 4 decomposed relation, and then we have find out. We have solved 2 examples based on that. Yeah.
So to satisfy second condition, for in every pair there must be a common attribute then, like R1, R2, R2, R3, R1, R3.
Yeah. See, if you take R1 and R2, there is no common attribute. Then you go for R1 and R3. There is also no common attribute. Then you go for R2 and R3. Right?
Yes, sir.
Yeah. If there is one more decomposed relation, say R4 equals to ABE, then you can take R1 and R4 because there is common attribute. You have to check all the possible conditions. If those condition is satisfying, then you can union those 2 tables. Like in this case, R2, 3.
Okay, sir.
So basically, we have to check the first condition, like for all the tables, and then when we are pairing 2 tables, we have to check the second and third condition.
Yes, yeah.
Okay, can we move further? Okay. Then we have to check dependency preserving or not. So attributes A, B, C, D, E, F, and the decomposition is A, B, C, D, E, and E, F. And the functional dependency are A, B determine C, D, C determine D, D determine E, and E determine F. So, okay. So first decomposition is R1 and the attributes is A and B. So you have to take closure, first A closure with the help of this parent functional dependency. So what will be the A closure? Anyone want to volunteer? Okay, no issue. So A closure will be A, and we cannot determine other functional dependency, and we have to take also B. So what will be the B closure? B closure will be B. Then in the R2 table, there are 3 attributes C, D, E. So first we have to find C closure. So what will be the C closure? C closure will be
C, D, and E.
C, D, E, F. So you have to take in those attributes present in R2 relation. So C, D, and E are present. So C closure will be C, D, and E. Okay. Then we have to take D closure. So what will be the D closure?
D and D.
D and E. Okay. So D and E. Okay. What will be the E closure?
Only
Only E. Okay. Then you have to take two attributes C, D. So what will be the CD closure?
C, D, E.
Okay. C, D, E. And we have to take then D.
Sir, closure of E should be E and F, right?
Closure of E. Yeah. Yeah. So, but closure of E will be E and F. But we have to see C, D, E, and E are present in R2. So you have to take in only those attributes present in R2 table. Okay. And what will be the DE closure?
D.
D. Okay. So yeah, D. Okay. Then you have to also take C.
E.
Yeah. Okay. C. So what will be the C closure?
C, D, E.
Okay. C, D, E. Okay. Then you have to take an E closure. So what will be the E closure?
E and F.
Okay. E and F. And what will be the F closure?
F.
Okay. Yeah. Okay. See. Then we have to see which functional dependency derived from child table. So see, C determine D. We can derive from this. We can say that C determine D. You got it?
Yes.
So this functional dependency is preserved in child table. Then we have to see D determine E is preserved in child table or no. So see, we can we can say that D determine E. So we can say that D determine E is preserved in child table.
Yes, sir.
Then you have to see E determine F is preserved in child table or not. See, from this we can say that E determine F. So E determine F is preserved in child table.
Yes, sir.
Then you have to see AB determine CD is preserved in child table or not. So you have to find AB closure with the help of this child table functional dependency. With the help of this. So what will be the AB closure?
Only AB.
Only AB. See, AB determine CD is not preserved in child table.
Sir.
So we can say that this decomposition is not preserving.
Sir, I didn't get it.
Okay, which part you did not got it?
AB closure.
Okay, AB closure. You have to find AB closure from help of this child table. So what will be the AB closure? We can say that A closure is so A. So we can say that AB will be A and B. There is nothing. So we can say that we.
Using AB we can't find anything. That is what you want to say.
Yeah. So this dependency is not preserved.
Sir, we are taking union of all F1, F2, and F3, right? Then we
Yeah,
can
yeah.
write AB as AB plus as ABCD, right?
Yes, yes, but yeah, we can take, but with the help of this functional, matlab, this closure, you have to find AB closure with the means. So what will be the AB closure? See, AB closure will be AB, only AB, not anything.
Then we're computing AB closure with respect to F1 only. I mean R1 only.
No, F1, F2, and F3, anything. With the help of only this child table, R1, R2, and R3. So what will be the AB closure?
Okay, we cannot see any B determines and A determines in the other two. So it's cut off like that. I mean,
Yeah, so this dependency is not preserved. So we can say that this
okay.
dependency is not preserved. I also gave one example in a Thursday session. You can watch.
Yes, sir.
So Hemant, yeah. So actually, what is the concept of dependency preservation is suppose we decompose one relation into R1, R2, and R3. So all that child table, not child. So parent functional dependency must be preserved in all the three decomposed relation here. Okay. So you can say C, D, D, E, and E, F is like that functional dependency is preserving, right, in R1, R2, and R3. But that
Yes,
AB
sir.
determines CD, we cannot derive with the help of F1, F2, and F3. If we can derive this AB determines CD with the help of F1, F2, and F3, means by combining all the functional dependency F1 union F2 union F3 and using some Armstrong axioms, so then we can say that AB determines CD is a dependency preserved. That dependency is preserved. But here in any sub functional dependency that F1, F2, and F3, AB is not determining anything, right? Neither A, neither B.
Yes, sir.
So we cannot derive that functional dependency.
Okay. I mean, there is no linking between AB and others. Okay. Thank you, sir. Sir, if the R1 is A comma B comma C, then we can find. I think we can get it right.
A comma B comma C.
R1.
R1.
Okay, let's find A comma ABC. Okay. So what will be the A closure? From the
A
parent
closure will
functional.
be A only.
Okay, A only.
B closure
So
will be B only.
okay, and the B closure will be B only, and C closure will be C only. What will be the AB closure?
AB.
Yeah, but we can say that ABC.
So C closure will be C, D, E, F, no?
Yeah, but you have to see which attribute present in R1 table. So only A, B, C is present.
Okay, got it.
Okay, so AB closure with the help of parent functional dependency, what will get? A, B, C, D. But A, B, C, only these attributes are present. So we'll get A, B, C. Okay, then yeah, we can say that if A, B, C, then dependency will be preserved.
Yes. So from ABC we can go to D, from D to E, and E
Yeah.
to F. So all are present.
Yeah, all are present.
Thank you, sir.
Okay.
Sir, here BC closure will give nothing, right?
BC closure will be okay. So what will be the BC closure? Yeah, will be only BC. Okay.
Yeah, so that R1 you considered ABC, right? So that trivially will determine ABC, right?
Yes.
From C we can determine D also. So AB determines CD, yeah.
Means to preserve the R1 should have CD both component, or R2 should have AB both component, right?
Yeah. So then how to preserve this functional dependency, that we'll discuss in the week 6, right? We'll go for another decomposition relation. normalization part. Okay. We'll see that now. So this is for week 5 based on a week 5 content. Okay. Okay.
Okay, if you have any doubt in dependency programming, you can ask.
Sir, if a function is FDs are dependency preserving, then does that imply that it will also be lossless?
No. No, these are two different things.
Okay, sir.
So that thing we'll discuss in the normalization part. If the decompose relation is in 3NF, then we can say that it is dependency preserving also and lossless also. But it is in BCNF, then we cannot guarantee that. Okay. So that thing we'll discuss and we'll also check that condition. Okay. Yeah.
Okay, sir. Thank you.
So I have still doubt in second part.
Which part? Second part means?
The second condition, sir.
In
above,
dependency.
yes, sir. In above page. Previous page, sir.
Okay.
Not this intersection part.
Okay. Yeah. Okay. Please tell what you have doubt.
So let's see if R1 and R2 in this R1 and R2 has no intersection, no common attribute in its intersection.
Yes.
And then we can say that second condition is not satisfied, or we have to check for other pairs also like R1, R3.
Okay. See, there is a decomposition A, B, C, D, E, F, and another is like B, C, D. So see, R1 and R2, R1. See, if we take this R1 and this R2, R1 and R2 returns null. But if you see this and this, R1 and R2, there is a common attribute.
Yes, sir.
So that's there will be. So second condition is
means any one of other
yes.
Any one of other decompositions would have common attribute with R1.
Yes.
Okay, sir.
Yes. Okay, Pradeep, do you want to continue?
Okay, thank you, Subin. So now we discuss about the normalization. So let me share my screen. Okay. Is it visible?
Yes, sir.
Yes. Okay. Before we moving to the discuss about the normalization, I would like to ask some question like what is so what is candidate key? What is primary key? And third is prime attribute. And fourth one is a non-prime attribute. Anyone would like to tell what is the candidate key, what is primary key, and what is prime attribute and non-prime attribute? Anyone would like to explain about this term?
Minimal super key is candidate key, and one of the candidates key is selected as primary key.
Okay. And what is prime attribute?
The attributes present in the
if A, C, A, B are the candidate key, so A is,
Yeah, prime
you
attribute.
means AB is primary key. Okay. This and this also may be possible. And what is the prime attribute?
ABC.
A,
A, B, C.
C. And suppose there
And
is a
all other
relation
attributes are non-prime.
A,
And
B
all
in
other are
relation.
non-attribute.
Yeah. In that you can see which is the non-prime
D.
attribute.
D.
D is the non-prime attribute. Yeah, right.
Yes, sir.
Okay. I think everyone get idea about this. What is candidate key and the primary key and the prime attribute and the non-prime attribute, right? Right. Yeah. So we're moving to the definition of that. What is normalization? So normalization, or we also said the schema refinement, is a technique of organizing data in the database. So the main goal of the normalization is eliminates the redundancy, and a systematic approach. Normalization is a systematic approach of decomposing the tables to eliminate the data redundancy and undesirable characteristic. What are the undesirable characteristics? That maybe this insert anomalies, update anomaly, and the deletion anomaly. Everybody aware about this? What is insertion anomaly? What is the deletion, update anomaly, and the deletion anomaly? Can anyone would like to explain? We previously explained about this previous session. Yeah.
Sir, I
Anyone?
would
Yeah, try at least.
doubt in insertion anomalies.
Okay. Anybody has the idea about the what is insertion anomaly, update anomaly, and the deletion?
So when we try to insert data, let's say like some other data is also required, which is irrelevant to the data which we insert. While
Yeah,
that is insertion anomaly.
Insertion anomaly, yeah.
And
what is
updation anomaly is when we try to update a tuple, we miss out some tuples because of duplication or
yeah, it may be possible sometime you miss out the update all the value, you remaining some of the attribute. Yeah, is that you mean, right?
Deletion anomaly. In deletion anomaly, when we want to delete an tuple some data, we'll also lose some other data which we don't want to lose actually.
Yeah, that is absolutely correct. Okay, let me explain it about. So now we see what is the insertion anomaly and the update and the deletion anomaly. So let me explain about, give little bit about introduction about this supplier ID, supplier relation. This is the SID, this is the supplier ID, and this is the city where the supplier lived, and this is the status of that city. And this is the PID is the product ID. What's the supplier supply the product, and this is the quantity. Okay, is it clear to you what this table is actually mean? Am I audible? Yes, right? Yeah.
Yes, sir.
And in so below of the table, it is given that the SID and the PID are the key. Means these are the primary key, right? SID and PID. Because only SID you cannot identify each rows, right? And so you have to take this and this SID and the PID. These two are both are uniquely identified each and every tuples, right? So here you can see in this SID is S1 and live in the Delhi city, and the status is this. And so what is the update anomaly? Suppose if the S1 is moved from the Delhi to, suppose, Kolkata, right? So you have to update this Delhi to Kolkata, and in this way, every instance of that where the S1 is there, so you have to update that. So suppose you update this one and this one to Kolkata, but you missed out these two. So at the later time, when you search for the where the SID S1 is belong to, so you get the two answer, and that is Delhi and the Kolkata. So it is redundant, right? So this particular problem is known as the update anomaly, right? And suppose you have to insert some other data, suppose S5, and that is suppose 5, and some city is Banaras. So you cannot enter this particular data because you have required at least supply one product. So suppose there you have to supply, then only you can insert this particular supplier ID. Is it okay? You understand this particular what is insertion anomaly, right? Am I clear to you this up to this particular point? And
if PID and quantity was null attribute, then we can insert.
But PID is the primary key. It cannot be null.
Okay.
Here it is given.
Oh. Yes, yes.
Okay.
Listen.
And what is delete anomaly? And as the previous someone said, I not able to get his name. So you can see some data is if we delete this particular data, suppose you have to delete this particular data, P1 and the where quantity is 245. So this information got also deleted. So in this way, you lose that information of the supplier, S3, and where he lived, and this particular status also you lose the information from the database. For you want to delete this particular data, due to that you lose this particular supplier information. That is delete anomaly, right? I hope it is clear to you what is the update anomaly, what is insertion anomaly, and what is delete anomaly, right? So yes or no, right? So we move forward.
So I haven't understood insert anomaly.
So here you can see, suppose you have to insert this particular supplier value, supplier ID, S5 who lived in Banaras, and this is the status ID of status of Banaras city, right? So you have to insert this particular value in the supplier relation, right? So for that you have to have that supplier ID supplier ID, at least one product should be supplied. But suppose he came to new on that suppliers, suppose that is a company, some company is there, so he joined new, he not even supplied an item. So for that time you have to keep that information in the database. So that is not possible, right? He have to supply some product P1 or P2, have to have. Yeah, up to this you followed, right?
Yes, sir.
And you get the what is insertion anomaly, right?
Yes, sir.
Okay, thank you. So next we discuss about What are the desirable property of the decomposition? The first is the lossless joint decomposition property, and the second is the dependency preserving property. So now come to the first normal form. What is first normal form? The first normal form should, every attribute should be single valued or only contains the atomic value. So as here you can see, a relation is in first normal form if and only if all the underlying domain contain atomic value only. So multi-valued are not allowed in the first normal form. You can see this C, the course there is, you can see that this is the multi-valued attribute. So multi-valued attribute are not allowed in the first normal form. Okay. So for that we simplified that that multi-valued attribute are not allowed in first normal form. So we simplified that. For that we give this particular value of the, for each value we give in the next row. Means for that we give in every row. So here you can see like the C name for this one is the one row, keep in the one row, and we writes the corresponding SID and the S name. Similar way for the C++, same thing is repeated. Here you can see. Up to this is clear, right? How to simplify this multi-valued to first normal form.
Sir, I have a doubt. We normalize a table to solve anomaly, right?
Yeah.
But sir, here in this case, if again, if we delete A, suppose S name A, then maybe we no delete means update. Then again the S1.
Suppose which one we you want to delete?
Sir, first row, S1 and A. Second attribute A, S name.
Yeah, this one, second row, first
No,
row,
sir.
and the
First row and the second attribute.
this one. So you cannot identify this uniquely, because if you want to delete, suppose you apply the where condition, SID is S1, okay, and S name is A, right? So it got deleted these two tuples, but you want to particularly delete this one, right?
Yes.
Yeah. For that you can see that this is not a primary key. Here it is a primary key. Now it is a primary key is what is SID and the C name. Both these two are composite key, right? After that you can identify this row uniquely. So suppose you want to delete this particular row, then you have to select these two attributes like C name equal to C. Yeah. Up to
Then
this
we
is clear.
we can update or delete the S name, right?
S name, yeah. Particular
sir,
which.
But
Yeah.
sir, in the previous case also where you discussed anomaly, also we have SI and PI. I think the both are primary keys. But we can you told us that in that case we can't update there. There should be one
No, which
problem.
one? This one. No, I said if you miss out this particular value during updated, then it will arise inconsistency in the database, right? You manually do row wise, right? Suppose if you do row wise updation, right, where S1 is S1 is for, it is not for the ideal case. Ideal case you will not get error. By chance, means by chance if you get updated manually row by row, then it will happen that where city is S1 city is Delhi, you have to update it to Kolkata, but you forgot to update that. Maybe possible, right?
Sir, means by hand we are doing that.
Yeah, by manually. I'm talking about a case, right? What is the concept about? What is the update anomaly? Okay. You get the concept, right? What is update anomaly? Maybe possible that suppose if you update this to Kolkata and but forgot this to update, then it arises the update anomaly, right? That is update anomaly. But if you're using the whatever's the PostgreSQL that PG admin, you will not get this particular anomaly. This is a concept, right?
Okay.
Yeah.
Means, sir, here we are doing by hand, not by program, right?
No, we are not doing it. It is a concept. You have to understand this particular concept, that what is update anomaly. You get that point, right? You want some application of that. I think you are looking for some example or the application.
Sir, I am getting confused about it.
Yes, Ashutosh. So if you see the first NF means, Pradeep, can you scroll down? Yeah, here you can see in this left table, CNAME has the multi-value attribute, right? So if you want to update that CNAME or some delete that, we cannot do it because it is multi-value attribute, right? So even if we apply the CNAME where condition, which value will get updated, right? Because it is a multi-value attribute. To avoid that anomaly, we decompose into, so not decompose, we convert it into a single atomic values, as you can see on the right hand side. So this table is in 1NF. Okay, it may be possible that we have removed all the anomalies, but it may not be possible that, okay, this like in update or insertion anomaly may still occur. So for that case, we go for higher normalization form. Okay, so that thing we'll discuss about the second normal form. So we need to decompose this relation into another two tables so that we can avoid that anomaly. Okay, so that Pradeep will explain that it.
I have a question over here.
Yes,
right now we are working with the PostgreSQL, but there are some other databases that provides the table under table. So this particular C++ is I'm inserting two, right? Two times. So my primary key is also two different primary keys also inserting over here. But with a single primary key, I mean, it's a multi-value, right? So if I have a table as a column in a particular CNAME, then only one S1 will be inserted for the primary key, and the rest of the value I can insert into it. So does it follow the exactly that first NF for that, or we are losing
yeah, so the basic condition for first NF is that the attribute must have atomic values only, right?
Yes.
So if you create a table which is present on the right hand side, as you can see, so then it is in 1NF because there is no multi-value attribute.
Okay, for the particular column, right?
Yeah, right hand side table.
No, not for the particular column, for the particular row.
Particular field that
particular
C++.
Yes.
We go for higher normalization form in order to avoid those redundancy now. Okay, so that Pradeep will discuss.
Okay. Then we need to break into the tables, right?
Yeah.
Okay.
So this table is only in 1NF. Okay, so still we are yet to discuss about 2NF and 3NF.
So, yeah, actually, I do understand. I mean, the whole data is in a single table, and we are trying to understand the first table.
Yes, Pradeep.
Yeah.
Please go ahead.
This particular student tables, you can see there is a multi-value dependency, and the SID is the primary key, right? After simplified, we get the SID and the CNAME. For that, how we simplified for the every multi-valued in the CNAMEs, for we keep in the new rows, right? Here you can see C and the C++ in this way. But the here one thing you can see, the SID in the student table is the primary key, but after that you can see S1 is not uniquely identify each tuples, right? So for that we combines with the C names, and these two combine can uniquely identify each tuple, right? So
Still some redundancy is there, though it's a primary key. Some
yeah.
values.
Yeah. So okay. So you can, this is the primary key. What is the definition of the primary key? Each can identify each and every tuples, right? So for that, you can see this.
Each and every tuple should be uniquely identified.
Uniquely identified, right? So,
and it should not be null. That is the condition.
Yeah. See, identify S name, right? This is the candidate key, right? For that. And you can also see the for the SID S1, this value is same. S1, this value is the same. This value is the same. This S3, this is, so we can say the functional dependency SID to S name is possible. We can write, right?
Yes, sir.
Yeah. So, okay. After that, you can see for the SID, this one, this value got repeated. For this one, this value got repeated. For this one, this value got repeated. A1. Suppose there one another S1 is there. For that S name will be same, and the suppose he took DBMS. So this particular value is a redundant, right?
Yes, sir.
This value is redundant, unnecessary, we take every time. So for that we simplified in the second NM. So so first we look at the definition that what is second NF. So a relation R is in second NF if only if R is in first NF. It should be in the first NF, means every column value should be atomic. Okay. And R contain no partial dependency. What is partial dependency means? Let R be a relation schema where X, Y, and A be the attribute set over R, where X is any candidate key and Y is the proper subset of that candidate key. Means Y is the proper subset of X, and A is a non-prime attribute. So what is non-prime attribute? As we discussed, that is not a part of that candidate key. That is we known as the candidate key, right? So then X
S name for the last table, what you have described. S name.
Yeah.
Yeah, S name one is the non-prime attribute.
Yeah. Thank you for that. So previously we can see in the functional dependency that what is that functional dependency? SID and C name can determine S name, right? And SID determine S name. So can you find what is the candidate key in this given FD, a functional dependency? Yeah. Anyone?
Sir, it is SID and CNAME, because if you take closure of SID and CNAME, it will determine SNAME also.
Yeah. This, so candidate key is SID and CNAME, right? And here you can see what is the partial dependency. Partial dependency means the proper subset of the candidate key, and this particular SID is the proper subset of the candidate key, right? Yeah. and it determines the non-prime attribute. Sname is a non-prime attribute. Therefore, there exists a partial dependency in that particular relation R. So in second NF, it is not allowed. So here you can see the above relation is a first normal form. We know that we convert it into the first normal form, but it contains the partial dependency. So to make it the relation in the second normal form, for that we have to remove the partial dependency. Is it clear to you what is partial dependency?
No, sir.
Okay. Here you can see this is the candidate key, right? Okay.
Yes, yes.
This is the candidate key, and this is the proper subset of the candidate. What is the proper subset of the candidate possible? SID is possible, and the CNAME is possible, right?
Yes, yes.
For this particular example, right?
Yes.
And you can see this SID determines something non-prime attribute, that is SNAME. SNAME is a non-prime attribute, right?
Yeah.
And this is the proper subset of the candidate key, right? And if this proper subset of any candidates determine any non-prime attribute, then it is called the partial dependency.
Okay, sir. Okay.
And that is not allowed in the second normal form, right? So we need to remove it. And how we can remove? For that, we need to decompose the tables, right?
Okay. Okay.
Yeah, now it is clear.
Up to this is clear, right? Okay. So this particular functional dependency we check by one by one, right? Alpha to beta. Suppose this is alpha to beta. What is the condition that this is this particular SID and SNAME is a proper set of a candidate key? Yeah.
No.
No, that is
No.
not
Because partial dependency is there, so that's why.
Okay. So this particular functional dependency is not a proper subset of a functional dependency. So this is not violate any the second normal form, right? So this is fine, but we have to check for this functional dependency. This is a proper subset of the functional dependency, and it violates the second normal form. So for that we need to decompose this particular relation. The relation contains following attribute: SID and SNAME and the CNAME, right? So first we decomposed into, for this particular functional dependency violates that second normal form. For that we make it as the candidate key, right? If we make this as the candidate key, so it not violates the second normal form. For that we make another tables R1, and we keep that as the SID and SNAME, right? And this contains the functional dependency SID, and we keep, okay, I think it is not visible. So here you can see the student table, SID, SNAME, and the CNAME, right? So we decomposed into R1, and what does that particular R1 contain? The first, this will contain. So what are the attribute? SID and the SNAME, right? if we make it the candidate key, this particular one, now is it violates the second normal form or not? Can anyone explain? Violates or not? So because this is the only primary key, the subset is not possible because it is the single attribute, right? So it not violates the second normal form. And for the second one, what we keep in the R2, R2 we keep only the SID and CNAME, right? In which the SID and the CNAME are the primary key, right? Or the candidate key. So what is the functional dependency it contains? We can derive this functional dependency, right? Using this one. So SID, SNAME, and we can derive this particular using this one. Whatever we attach to the SID, if SID determines SNAME, and whatever the attribute attached to this SID, that will determine SNAME, right? Up to this is clear, right? What is any problems in the
Yes, sir. Yes, sir.
Okay. So we decompose the S and in this particular where the SID and the CNAME is the primary key, it's the R2. This is the primary key, and for this is the primary key for R1. So now we can check this as a functional dependency diagram, and that what are the functional dependency possible? You can see here SID and the PID both are FDR, SID, PID determine quantity, and SID to
Status. SID to city.
And SID to city.
City to status.
And city to status, right? So can anyone tell what is the candidate key in that particular functional dependency? You already aware about how to find the candidate key, right? Simply you have to check which of the following attribute is present on the right side or not. So you can see status is present, city is present, and this
SID and PID.
Quantity is present. So these two are mandatory. That should be present on the left hand side because no other functional dependency derives them. So SID and PID.
PID combined.
Yeah. So find the closure of that and what SID and so PID. Right. After that, SID to status and the city and city to status. You can find all the attributes from this. So these two are the candidate key, right? Together.
Yes,
okay.
Sir.
Okay. So candidate key is SID and PID, right? So after that, check one by one. This is a proper subset of a candidate key. No. So that means this is in second normal form. After that, we check this is the proper subset of candidate key. Yes, this is the proper subset of candidate key. So it violates the second normal form. Similar way, this is the proper subset of, yeah. Is it clear to you? Means how this is not in the second normal form? Because this is the partial dependency is there. Okay. This is not the proper subset of the candidate key. So it may be possible in the second normal form. So we decompose the tables into this particular tables into two decomposition. If you are facing any problems in regarding how to solve this, you can ask. So in the R1, you get this one SID, PID, and the quantity. So these two are the candidate key, and the second R2, you get the SID, PT status. So here, what are the functional dependency? SID to status and the SID to CT.
CT to status.
And CT to status. In that particular, this SID is primary key, right? Candidate key, primary key. Okay. And CT to status. Okay. And this particular for this SID and PID is up to this is clear, right? So you can check there is this is how we decompose the from the decomposed in the second normal form. Now you can see this is the free from the second, this is in the second normal form. So we check for any further any redundant, it contains the redundant or not. For that you have to check. So here you can see that okay, this is SID is a city and city have the status. What I have said that this particular attribute is the supplier ID and where the supplier lived that, and this particular is the status of that city. If any other supplier came, that's the S5, and he lived in that Delhi, right? And so this status is this is the status of Delhi. So every time we write the city as a Delhi, the status should be same, that is 3030. So that is the redundant also. That is redundant attribute, right?
Yes,
so
sir.
Every time we repeat the Delhi, so the status is same. So that is redundant. But we do normalization for reduce the redundancy. So for this to deal with that, this is the free from this is in the second normal form. So further we can see there is a redundant also. So for that we use the third normal form. Okay. So this is the third normal form. What is the third normal form? Let R be a relation schema, relational schema, and R is in 3NF. Only for R should be in second NF. So it should be in second NF, and R should not contain any transitive dependency, or every non-prime attribute of R is non-transitively dependent on every key on R, right? So this is, we can summarize this particular part, and we can only check, it is also, we can check that's third normal forms. Suppose there is a functional dependency that X to A. So if A is a trivial dependency, so A is a subset of A, then we can say that is an third normal form. And if basically if it satisfies this three condition, then we can say that's the relation R is in third normal form, right? So for that, the functional dependency like X to A, if A this functional dependency is trivial, then we can say this is in third normal form. If A is a super key, then we can say this is in third normal form, or maybe it is possible A is a prime attribute, right? So for the above case, we can see up to this we simplified the second normal form, but we can see in that particular SID to CT and the CT to status, it contains the redundant. So we need to simplify that. And one term is, there is the transitive dependency. You can see the transitive dependency. Are you aware about what is the transitive dependency? Can anyone explain this particular term?
Like alpha determines beta, beta determines gamma, then alpha determines gamma.
That is transitive function, right? I'm talking about the transitive dependency. Okay, so you partially right? This is, suppose this is the candidate key. Okay, so if the CK is, this is the candidate key, alpha is the candidate key, it determines beta, and this beta is determines another non-prime attribute. If non-prime attribute determine another non-prime attribute, that is we call as the transitive dependency, right? Am I clear to you? Right?
Yes.
Yes. Okay. It should be that if non-prime attribute derives another non-prime attribute, so then we call as the transitive dependency. For that, in the third normal form, it is not allowed. We are not allowed that transitive dependency for in that particular. If we consider only that case, only this part, because it is in the second normal form, and also we check this particular is a super key, right? If it is a candidate key, then it is also super key. So what we have said is, the three condition is what? If left side is a super key, then it is a third normal form, or right side is a prime attribute or not. So this quantity is not a QTY, means quantity is not a prime attribute, right? So it satisfies one condition. So that means it is in third normal form. So similarly, we have to check this particular, this is a candidate key. We're checking for the third normal form, right? So this particular SID is a super key because this is a candidate key. So it is in third normal form. This SID for this, the left hand side is a super key. So this is also in the third normal form. But we have to check if city is a super key.
No, sir.
City, no. After that, we check for the next condition that status is a prime attribute or not. Status.
No.
No, because this is the only one candidate key, right? So this is not. So it violates. It is in second normal form, but not in the third normal form. This particular. So we need to remove. So this is the transitive dependency. You can see SID determines city, and this is the city is a non-prime attribute and determines another non-prime attribute. So that is that we are not allowed in that third normal form. For that, we simplified. We need to further decomposition to be in third normal form. So let's take this particular example. R2 SID city status. This is fine. Only you have to. So for that, you have to decompose. So this particular violates the functional dependency, third normal form rule. So for that, we have creates the another decompose this particular and makes this as the candidate key. So R3, where the attribute are status, and here the city is a primary key, and this one is for this one we can write so up to this you get. Let me clearly write this as here. Let me write R we decomposed into in R2 contain SID, city, and the status, right? And the R4, R3 contain city and the status, and R4 contain SID, city, and this contain SID and can anyone explains the what are PIDs? Can you check for this R1, R3 and the R4? Does it preserve that lossless decomposition or not? We can check, right? So for this, first we have to check R1 union R2. So it contains SID, PID, QTY, city, and the status. So I think it contains all the attribute SID.
Yes, sir.
All attributes, and we have to check for what is the common attribute.
SID.
Oh, for this. Oh, okay. check in the another way. So first we have to check this R3 and the R4. So we can order.
Status.
Okay, first we have to check for the R3 union R4, right? So what we get? City, status,
SIDs.
So equal to dot.
And SID, and that is equal to this particular R2, right? R2, yeah. And for this, what is that R union R4? R intersection, that is city.
City.
Yeah, and we make it as the, I forgot to mention that. Okay. And this city is the key or not in the either R1 or the R4, R3 and the R4. It is a key, right? So
yes.
That means that is R3. So this particular are lossless decomposition, this particular, and we have to check overall, right? So now we have to check for the R1 union R2 or okay, right? So we got this city, status, and SID, and PID and the quantity, right? So this equal to R. Yeah. Are you able to follow me or not? R1 union R2, right? And so the R1 intersection R2 is
SID.
SID. And SID is a key. SID is a key in this particular R4, right? R2.
Yeah. Yes.
Yeah. So it determines R2, right? So it is a lossless decomposition, right? What we have done. So we can conclude the R3 as the R3 is a lossless decomposition. Can we say that the R3 is a lossless decomposition? 3NF is a lossless decomposition. We just prove it, right?
Yes, sir.
Okay.
Sir.
So here R2 is a lossless
no, R2 not. I said that R3 is this particular, whatever the R we decomposed, are decomposed into 3NFs. So we can say that the 3NF is a lossless decomposition, right?
Yes.
Yeah.
Sir.
Yeah.
Sir, let's say I have a candidate key AB for a relation. And,
okay, first tell me what is your relation, what are the attributes present in relation?
So ABCDEF.
Okay, I think this is clear to you. So can I erase this?
Yes.
Okay. What are the attributes?
ABCDEF.
A, B,
CDEF.
CDEF, right? Okay.
So now let's say the candidate key is AB.
Okay.
So A and B are the prime attributes.
Okay.
So if there is a functional dependency stating AC determines E. AC determined E.
Okay.
AC. So is this AC a non-prime attribute?
No, So first tell me, what is your complete functional dependency? How can you come at to this point that AB is a candidate key?
Sir, I mean, I have a set of functional dependencies. From that, I counted, I mean, I calculated this to be the candidate key.
Okay. Okay, these two are a candidate key, right?
These two together is a candidate key, yes, sir.
Okay.
Together, not A and B. No, they, I mean, you cannot further, then it will not be a candidate key if I can further divide them. Like if A can be a candidate key, then A cannot, AB cannot be.
Okay. I get your point, right? This for after computes the candidate key, you get this particular attribute, means composite A and B as the candidate key, and so you have this functional dependency in that functional dependency.
Exactly, sir. Exactly, yes, sir.
Exactly. Okay. So the attribute, whichever attribute present in the candidate key, only that attribute are the prime attribute.
Yes,
So
sir.
here what is present? A and B. So prime attribute is A and B, right? So C is not that prime attribute. That is a non-prime attribute, right?
Okay, so I mean, it doesn't mean that if it is associated with a prime attribute, so it will also.
No.
Okay, sir. Thank you. So sir, if AC is a non-prime attribute and let's say E is also a non-prime attribute, so this will be a transitive relation.
No. That is not transitive relation, because first you just imagine that a situation for that it may not arise. For that's why I ask you that. Tell me the complete functional dependency.
Yes, sir. I am giving you the functional dependency.
Okay. So let me complete the BCNF part. After that, I get.
Okay, sir. Okay.
So up to third NF is understood, right? So what is BCNF? A relation schema R is in BCNF with respect to a set F of functional dependency if for all the functional dependencies in F plus of form X to A, where A is a set of attribute of R, means A is a subset of R and X is also subset of R, at least one of the following condition hold, right? And that is, first, if X to A is there, so this functional dependency, if this is trivial, that means that is in BCNF. And second is, this X must be a super key. Okay. For this, X is must be super key. So can you tell me what is the difference between the third NFs and the BCNF? Anyone?
Sir, third NF said that I mean the left hand side should be non prime attribute, and BCNF is stricting it and saying that it must be a super key.
Okay. Let me repeat your statement, right? So for that, X is functionally determines A. For left hand side in the, what is the condition on the third NF? So this functional dependency is a trivial functional dependency, or this is a X is a super key, or A is a prime attribute, right? This is the condition we have. We just,
yes,
here you can check it. So you can check this particular is a trivial functional dependency, or X is a super key, or A is a part of some candidate. That means A is a prime attribute, right?
Prime attribute, yes, sir.
Yeah. But in the BCNF, we restrict that part, that
Okay.
whatever present in the left hand side, that is must be a super key, right? And that is the difference between third NF and the BCNF. So we can say that the BCNF is a stricter form of the third normal form, right? We can say that.
Yes, sir. And every BCNF is in 3.
Yeah. We can conclude that also. So we can conclude the lower level, means what you have just said, that the first normal form, second normal form, and the third normal form, and the BCNF, right? So the functional dependency which is in BCNF, that is also in third normal form, and that is also in the second normal form, and that is also in first normal form, right? But you cannot say if that's the functional that relation are in that functional dependency are in the third normal form, that is may or may not be in BCNF, right? You have to check that. Am I clear? Am I clear, right?
Yes. So this is the condition of the third NF, and what is the condition? So X must be strictly a super key, whereas in third NF it can be or cannot be.
Yeah. If this is not super key, then there is another condition in the third normal form, that if A is a prime attribute, maybe A is the prime attribute for if that particular condition satisfied, for that it is in third normal form. Yes.
Yes.
Yeah. So, but in the BCNF is a way strict to that the X must be a super key, right? For that, we only remove the second condition, right? That A is a prime attribute. Okay. Up to this is clear, right? What is BCNF? So we took another example. We take another example that suppose this is the functional dependency. Student and the course to instructor and the instructor to course, right? So what is the candidate key? Can you tell me?
Student, sir.
Student. Let me take the closure of student, right?
No, sir. Student and course together is it?
Okay. This
Student
together
course
are
combined.
okay. So these are the candidate key, right? So so you have to check for the it is in third NF or not. So how do you check? Anyone would like to? How we check? We just discuss about that. What are the condition for the third NF, right?
Sir, student and course is a candidate key. So student course determining instructor is okay. There is
Okay, means this is in third normal form, right?
Yes, sir.
Yes.
And
Okay.
in the second functional dependency, course is a prime attribute. So this is also in third normal form.
This is also in third normal form. Let's check for the BCNF.
Yes, sir.
So tell me for the first normal form.
So student and course is a candidate key. So of course it is a super key also.
Okay.
So it is
that
in
means
BCNF.
BCNF, right?
BCNF, yes.
And for the second one?
Instructor is
Instructor is not a part. not a super key.
I mean,
So
we
Not
have
not a super key, right?
no.
So it is, so you can see this is in third normal form, right? But
Yes.
not in
BCNF.
BCNF, right?
Yes, sir.
For that we make this to the BCNF. So why we do the BCNF? BCNF is a less redundant, right? Than the third NF, right? For that, but for that you have to remember that for that BCNF only. Let me write. Okay, BCNF guarantees the lossless decomposition, right?
Lossless decomposition. Yes.
But not guaranteed that functional dependency.
Yes, sir.
Preservation of functional dependency, right?
Preservation of, yes, sir. Yes, sir.
Yeah. Okay, so where we so this particular violates the BCNF condition, right? For the BCNF, so we make it so we decompose for this one. So this you have to remember that. So particular function, this x to a, this functional determines if this particular function violates the BCNF. So what we do, what is the formula for that decomposition? So this is AX. So this is one decomposition, right? And the second one decomposition is R minus A. And what is that? R1 is an instructor or instructor. So here you can see, you can relate with this formula, right? So R1 contains instructor and the course, right?
Yes, sir.
And the second one, what it contain? This particular minus, you can see the formula. So what is that? Student
And course.
and instructor, right? Up to this is clear, right? BCNF, how we decompose, what is BCNF, how to we decompose the BCNF. Right. Yeah. Up to this is clear, right? Normalization part, what is first normal form, what is second normal form, what is third normal form, what is BCNF, and what is update anomaly, what is deletion, and the insert anomaly.
Yes, sir.
Yes, and okay, so we come to your question. What is your question?
Sir, before that, so is this this is not preserving all the functional dependencies, right?
Yeah.
Yes. So
may or may not be.
okay.
Right.
So we, I mean,
that's why we said the not guaranteed. Yeah.
So, so whether we will decompose decompose a relation in in BCNF or not, that will depend if it is preserving the functional dependencies, right? I mean, if it does not, so there is no point in decomposing it.
Maybe some use of that. So if you want some your system less redundant, right?
Yes, sir.
For that you compromise that functional dependency, right?
Okay.
Suppose univ as required.
So it depends on what my use is.
Yeah.
Okay.
Sir,
Okay. Yeah.
in R2, how is instructor the only key?
What?
In R2,
Please.
where you have written how instructor is the only key. Student and instructor should be combined and become a key.
No, I not writes that is the key. I just, okay, these two are, okay, these two are the combined candidate.
Yeah, yes.
And this is also not a candidate. I'll just write that. Okay. Okay. Up to this is clear, right? So any
Yes.
doubt, any question? So
Yeah. So any doubt? I guess you can watch the content again and solve the activity question. We can take this in the next session also, right? The same content we can take if you have any questions. So please go to the activity question, watch the videos again. Okay, we can take this normalization part in next session also if you have any doubt in this.
Okay, sir. Sir, the question I had, so should I tell it or in the next session?
No. You can tell it here. Yeah. You can ask.
Okay, sir. So the functional dependencies, I was talking about a functional dependency and whether it is a transitive relation or not, transitive dependency or not. So the functional dependencies are, sir, AB determines C, AC determine E,
okay.
and EF determine D.
EF.
F, yes sir,
Only F or EF?
EF, sir, EF. EF determine D.
Okay. EF determine
D.
E.
D, sir.
What? Okay.
Delhi.
Let me write A, B, C, D, E, F, right?
Yes.
And that is Delhi.
Yes, sir.
This
And
is
AB determine F.
AB determine F.
Yes, sir. F. Yes, sir.
What are the candidate key? You
So
can check.
I calculated the candidate key to be AB.
Okay, let me check. Okay, for this particular closure, we get this AB closure, right?
Yes, sir.
And after AB closure, we get the ABC closure. And from this, and from
Yes.
this, we get AB,
CE.
BEF, right? And from the AC, we get E.
Yes, sir.
A, B, C, E, F, right?
And from
Hence
that,
the EF we get D.
yes, sir.
Right.
Yes,
And
sir.
that is equal to R.
R.
And this is not present in the right hand side, so it must be appear in the candidate key, right? So this is the only possible candidate key.
Yes, sir. Yes, sir.
Okay. So now we check for, is it that particular functional dependency whether in third normal form or not, right?
So, sir, my question is not whether checking it is in third normal form or not. I'm just asking that if AC determining E, is this a transitive relation or not? Like EF determining D is a transitive relation. We can say that very well, that EF is a non-prime attribute, D is also a non-prime attribute as well. So this is a transitive relation. But AC determining E, is that a transitive relation or not?
So let's stick to the basic. That's the definition of the transitive dependency is what? Non-prime attribute is determines the non-prime attribute.
Yes, sir. Yes.
So we can say that for this particularly.
Yes.
For this, whether we have to check this is on in that. Let's check. So we have to check for the is it in the second normal form or not.
Okay.
We can say that A, B, C, E, F, right? And this one contains that E, F.
EFD.
Window?
EFD.
EFD, correct? And after
Yeah.
and this particular contain
And another
EF to D, right?
Yes.
And this contains the AB to C, C to E, and AV to F. Okay, for this, so we need to further decompose this particular. So what is your approach to solve this particular? I have to come to you this particular letter, right? So can you post in Discords? So I.
Okay, sir. I will.
It will, yeah. So any other doubt?
Hello, yeah. Is there any other question? So please go to the lecture and solve the questions again. Okay. I can see some of them have, some of you have few confusion in the normalization concept. So again, we can again discuss it in the next session. Okay. So, but first, please watch the videos and solve the activity questions also.
Thank you. Have a good,
Thank you,
good
sir.
day. Have a nice day.
Yeah. Thank you, everyone. Have a nice day.
Thank you everyone.
Thank you.
Thank you, everyone.
Thank you, sir.